Hello everyone. So today we will be doing this number theory problem, which is on like exponents basically. And I saw this problem in a class 2 days ago, and I liked this a lot, so I thought to record a video of it. So let's begin. I'll first explain the problem. Uh, Consider n positive integers a1 to an. A1, A2, so on till an, at least two of which are distinct. Prove that the sequence, this sequence basically, has infinitely many prime divisors. So what does it mean to like say that this sequence has a prime divisor? So we have to prove that if pi is a prime dividing some term of this sequence, let's call this sequence S. It divides some term of this sequence S, then we say pi is a prime divisor of that sequence, and we have to show there are infinite such primes. And we have these. Okay, now how is this sequence defined? So, yeah. So we are given n fixed integers. So we already have these integers a1, a2, so on till n, and we consider the terms a1 plus a2 plus so on till n, a1 square plus a2 square plus so on till an square, a1 cube plus an cube, and this continues, and the kth term is basically just a1k plus a2k plus so on till ank. And yeah, this is the sequence. This is basically what this notation means. Some people consider it like set of some number or something. I saw this today, so don't do that mistake. Yeah. So how to begin with the problem? So contrary to what we have to prove, we assume that this sequence, we will call it S in our whole question. Assume S has finitely many divisors. Say P1, P2, so on till PT. Now, what we can do is we have like an infinite set, and this is like a nice idea which I was taught, that we can put some constraints on our infinite set and still keep it infinite. This is the nice property about infinite sets. So what we do is let's consider this prime P1. Now P1 will divide either some finite terms, finite number of terms in S, or an infinite number of terms. Or all the terms. Like infinite thing is just a subset of this, but let's just assume these are the two cases right now. Okay. Or a better way to say this is like, okay, I'll write it in a better way. P1 divides a finite number of terms in S. Second possibility is P1 doesn't divide finite number of terms in S. Third is P1 divides all the terms in S. What we do is, in either of these two cases, we remove the elements which are divisible by P1. So if P1 divides finite number of terms in S and we remove some finite number of terms from S, we still have a finite set. But what's the property of this set? This set will have like prime factors from P2 to Pt. We have reduced like the number of times we are dealing with in some way. If P2 does not divide a finite number of terms in S, what we do is we remove those finite number of terms, and now P1 divides every term in S in like our new S. We can call it S dash after removing the element. So now P1 divides every term in S dash. And if this is true, we just don't do anything with P1. So in this way, we continue, and we can get a new set S dash such that there are some K primes, let's say. All these primes divide each element of S dash. This is our new S dash. And note that S dash is still an infinite set, as I showed above. Yeah. So now what do we have to show? We have to show that this sequence has infinitely many prime divisors. So what we do is, uh, let's just consider this term. Okay. Let's consider ai to the power. Oh, k is already there in the question, so I can just do it. Nice variable L, let's say L primes. Okay. Now, if we consider ai to the power k mod pi pj, let's say, then note that this k we can pick. Like k is arbitrary. All right. Uh, yeah. So can we like find a nice thing like ai to the power k is congruent to c mod pj? Can we find a k such that this c is nice? Okay, one nice thing it can be is note that if pj divides ai, in this case ai to the power k is just 0 mod pj. Can I find a nice k such that if pj does not divide ai, then let's say ai to the power k is like just a fixed number mod pj. This how it will help us, I'll show in a bit. But right now, like it should be intuitive that this number can be like 1. By Euler's theorem, if you pick k to be phi of pj, then this always holds, right? If pj does not divide ai, right? So this is a nice property. If pj divides ai, then this thing is 0 mod pj, and if pj does not divide ai, then this is 1 mod pj. Now, can we talk about this thing? Sigma ai to the power k modulo pj. Note that there are n terms in this sequence, and we pick a the k picked here is nice k. We just talked about how our nice k looks. So we said that above that k, if k is phi of pj, then we have a nice characterization about ai to the power k mod pj. So let's just pick this sigma I equal to 1 n a I phi pj. Yeah. So note that this thing is always less than n modulo pj. Less than or equal to 1 basically. Why so? Because there are like n terms in this sequence. Each other term is either 1 or 0. And it's greater than equal to 0 also. Okay. So we got this. But the thing is, it doesn't let us bound, one possible, why it doesn't let us bound anything. Consider the case when, let's say, n is pj plus 1, let's say. In such a case, we have that sigma I equal to n, or okay, let's just say k pj plus 1, ai to the power 5 of pj is less than equal to 1 mod pj. Now the thing is, this thing, it can be anything, sigma ai to the power 5 of pj. It can be like, what do you say? Some, let's just take some. It can be, x times pj plus 1, which is very vague. X can be as large as it has to be. We do not get anything useful. But if we note one thing, if we pick uh, this modulo, this equation which we had, okay, I'll replace this by k here once. If you pick some large enough pj such that, okay, large enough, you can say modulo number, I'll call it, tell a nice variable. Uh, let's just say m mod n. If I can pick a large enough m such that n mod m is in the like lowest form, like n is the lowest possible number, positive, and then I pick a nice k for this m with this characterization such that this inequality which we had, this will still hold. We will get something nice. How to do this? Flight note sounds big. I'll tell you like rigorously. Pick alpha j such that pj to the power alpha j is greater than n. Then, if we consider k equal to phi of pj to the power alpha j, then sigma I equal to 0, oh sorry, 1 to n, ai to the power k is less than equal to n mod pj to the power alpha j. Why is this true? Because anything to the power phi of pj to the power aj is just 0 or 1 mod this thing. So this is a nice thing now. But the thing is, we have only dealt with one prime here, pj. Let's deal with all the primes. So uh, let's consider p1 to the power alpha 1, p2 to the power alpha 2, so on till pk. Okay, let's say the primes which we have. Okay, L we took, right? So consider p1 to the power alpha 1, p2 to the power alpha 2, so on till pl to the power alpha l. Let's call this number m, capital M, and we take our k to be phi of capital N. Then sigma I equal to 1, I equal to 1, yeah, n a to the power k, a to the power k is less than n, less than equal to n mod n, right? And this is less than equal to, greater than equal to 0 basically. Yeah. So why is this true basically? AI equal to phi to the power n. Mod n, so this should be 0 or 1 only, right? So now this is less than. Um, okay, yeah. So I got a bit confused here. What I meant to say is, we have this thing also, but we do not need this actually. Instead, we can consider this mod, let's take pj to the power alpha j, and this is true, right? K is fixed here. So now, if you notice that since this is less than equal to n mod pj to the power alpha j, but this is like, greater than equal to 0. What if this thing is 0? What if this thing is equal to 0? Sigma I equal to 1 and ai to the power k is 0 mod pj to the power alpha j. Then it's possible that this thing is just equal to pj to the power alpha j, which is will be like ultimately greater than n. So we cannot bound still. We need to remove this equal to 0 case. Okay, how to do this? If I go back to original problem, do you see that I can basically assume here that GCD of A1, A2, so on till An is just 1. The reason is, let's say the GCD is D, then every of these terms, let's consider this term, sigma I equal to 1 and AI to the power K. We can write AI as D times BI. This will be equal to D to the power K into sigma I equal to 1 and BI to the power K. And now note that D always has a finite number of prime divisors, and we just have to work with this sequence now, right? A finite number of fixed prime divisors, basically any power of D we have. So we and GCD of BI is just 1. So we can just assume directly that their GCD is 1, right? Okay, ignore this. We had that 0 less than equal to sigma I equal to 1 and AI to the power pi of m, where our m was that product of primes and powers of that, like pi of pi to the power alpha less than equal to n mod some pj to the power alpha j. This is what we have. If this thing is 0, it means pj to the power alpha j, it basically means like pj to the power alpha j divides ai, or simply you can just say pj divides ai, which means that GCD of a1 so on to an will be like, pj times something, but we assumed it is 1, so this is not possible, right? So we get that this thing cannot be 0, and hence it's always greater than 0. Now this is a very nice thing. Why? Because this tells us that vpj of ai to the power phi of m is always less than or equal to vpj of n, right? And now if we consider this for all primes, right? If we consider pi j equal to 1 to L vpj ai to the power phi of n. Also, this is like, sigma less than equal to pi j equal to 1 to L vpj of n. And do you realize this thing is just a constant? Let's say it's capital C. So we get that pi of Vpj sigma ai pi to the power n is less than equal to a constant. Now, what is this thing now? Like you are multiplying the prime powers, right? Wait, do we need to multiply the prime power? Uh, okay. Uh, we can. I think we can do it in a better way. Just a second. Okay, yeah. We basically do not consider this thing. Ignore this. Oops. 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 Yeah. Instead, we consider pj to the power vpj of sigma ai to the power phi of n less than equal to pj. This follows from this pj to the power vpj, and then we consider, you know, the product which we did in the last one, and we can take product of this over all primes and product of this over all primes. Notice that this thing is just a constant. Let's say it's capital C, and then which means since 1 to L are all the primes dividing this term, as we just said, this thing is just equal to sigma ai to the power phi of m less than equal to C. So we got that this thing is bounded, but it still doesn't finish. It's possible that it's bounded, right? Notice that if yeah, if here I take my k as q times this. Let's take a just a black. If I take my k as q times this, then this thing will still be true because this is true, right? And this equation will also be true, and ultimately this will be true, and all this we did, it is still true. We just get it's a factor of q here. Q can be anything. Make q large, and eventually make q so large that this is greater than c. It is possible because you are increasing q. It's an exponential series, right? But this is not true because this should hold, as we said, if there are finite primes, hence a contradiction. So yeah. So basically, we finished the problem. I'll give a quick overview of what all we did. First of all, for contradiction, we assumed it has finite prime divisors. Then we put some constraints on our set S so that we got that these L primes divide all the terms are like basically the set of all prime divisors S dash has, and each of them divides each term of the sequence. Okay. Then we tried to consider mod pj, but mod pj doesn't give us any bound. So we cleverly pick pj to the power alpha j such that it's greater than equal to n. It's greater than n basically. And then we put mod pj to the power alpha j and pick a nice k such that we get this inequality. And then we pick all the primes we can consider so as to like keep the k fixed in while considering different primes. Else it's very messy. I mean, I don't think so you can do it otherwise. If you like just analyze for individual primes and do not combine them, obviously. So now this thing is true for all pjs and our k is fixed here. And then we basically instead of from this thing we got this thing to be true, this box thing, and then we magically brought this q. And since q can be any natural number, we just take q large enough such that this holds eventually because c is a constant and you can do this, which is a constant contradiction. So I hope you enjoyed this problem and I like this problem lots, so I thought to give the solution. For the next video, I'm planning to do a part 2 of the rational points thing. I'm planning to do a talk on showing that rational points on a cubic curve form a group. I have taken a class of that in Sophie Fellowship, and I'm planning to upload the same lecture on YouTube. Let's see when. Thank you for viewing the lecture. Have a nice day. Bye.